All right. So what I wanted to talk about today is a tool that's kind of picked up some interest in the Haskell community, but I don't think has really been bitten on by Scala users, mainly because they don't know it's there. Which are these something we're going to call a lens here, and I'll actually give a definition as we go. But the general kind of 10,000 foot overview is they're like the functional equivalent of a reference. Okay, and we'll go from there. And so the title of the talk is Lenses, a Functional Imperative. I was fiddling around with various names for this talk when I put it together. I wasn't quite sure if it should be functional and imperative, or if it should be somewhere here. Imperative and functional. Or, so. But, so basically what I'm going to talk about is sort of what is functional programming. Just talk about field accessors that we use in sort of day-to-day, Java / Scala / functional programming programming in general. I want to define what lenses are, and then I'm going to go back through the state monad and some uses of lenses with regards to state. Okay. So if you don't know what a monad is, don't worry, it's not critical of the talk. Okay. We're going to use them. We're not going to actually care too much about definitions and laws and such. So, what is functional programming? Well, I think Runar gave a talk back in January when he summarized it more or less by saying that we have no side effects. And then he went on to give a much longer-winded explanation in terms of referential transparency and, an expression E is referentially transparent in a program P if you can turn around and replace the expression with the value that is the result of that expression. And not change the meaning of your program. Okay? And then we can build a definition of what a pure function is by taking this sort of referential transparency to a sort of logical extreme and say that a function is pure if when you apply it to a pure argument, you get referentially transparency. Okay, and then when it comes right down to it, so to define what functional programming is, functional programming is the art of programming with pure functions. Okay, so we're not going to be using exceptions because I can't throw an exception from a value. We're not going to use I/O because that would, depending on when I caused the effect to interact with the real world, I would get a different answer. And I've lost some mutation and some things that I'm used to actually leaning on. Okay, so again, kind of, so what do we lose and what do we gain? We give up mutation, exceptions, I/O, and we gain easier parallelism. If I don't care when something happens, if I have a pure computation and a pure value, I don't care where I compute it. I don't care about when I compute it. So I can send it off to Nerman's remote functional application server and it'll work just fine. Or I can run it in a background thread or fork join or do whatever I want to these values or these computations, and I don't really care. It's easy. I get fewer bugs because I have fewer places for bugs to hide. And we get this tool for reasoning is that we can use what we call equational reasoning, which is that I can literally replace sort of, if I say f of x equals something on the right hand side, I can reason about that equality like a mathematician reasons about equality. I can replace what I see on the left hand side with what I see on the right hand side, and I don't change any meanings. So we have we've all written code that changes member values and objects. We build objects, we keep them around, we tweak their contents. But setting a value, setting a field to a value is actually a side effect. So in Scala, we tend to copy the object instead of, and replace the one value that we wanted to change with its new result. And Scala, yes? Scala makes this really easy for us with case classes, which kind of bake in this functionality. We could go off in a fairly, I don't want to say, this isn't very Java-like because you would usually wrap it in some sort of getter and setter and all that stuff. We wouldn't actually give you direct access to the field. But we could make a mutable pair class and give it a couple of vars that we could set directly and read and write. And then we could define the sort of the automatic wrapping and unwrapping of this. So we can construct it just like we can construct pairs or products or what have you. But in practice, we just tend to use something like pair, or the built-in product type, which gives us the accessors _1 and _2. And then if we wanted to change one of the values but not the other, we would give you a new pair, usually by using the copy method, which is provided for us by Scala when it compiles any case class. Okay, and so when it defines copy for pair, it kind of behind the scenes builds us a method that looks like this, where it's going to turn around and take two name parameters which have the same name as its arguments, and it will give those default values equal to the current contents. So I can use named arguments to the function, and this will use _2's value from foo as the default value. That's sort of how we would, if we had like a 50 argument case class, you can see how copy saves us an awful lot of work in just turning around, and otherwise we would have to say, bar equals, I want a pair of foo.1, foo.2, foo.3. All right. But mutation is, well, pretty damn convenient, because when we start changing fields of fields, copy kind of breaks down on us. It doesn't really work very well here. We started, if we wanted to compare it to sort of using sort of mutation directly, here we can just say, hey, foo2 equals 4, right? We can mutate nested deep. We can go inside of a mutable pair, or a mutable pair and a map inside of a pair, right? We can go arbitrarily deep into things that we can mutate, and it's really easy. I think the Eiffel guys way back in the day might have gotten mad at us about violating the law of Demeter or something, but we would be okay. The language doesn't get in our way. But here, we're repeating ourselves when we start using copy, because copy is going to make us start talking about foo._2 in two different places in order to go two levels deep. If I go deeper and deeper, I'm having to say more and more stuff over and over and over again. Okay, and I'm actually doing this sort of dereference twice, and it's generally an obnoxious solution to the problem. Okay, so this is one of the reasons why functional code tends to generally not deal with lots of nested structures that it has to pull apart and take back, pull apart and then put back together. Mainly just because you pay this tax. Okay. So again, copy doesn't compose. So that sort of leads us to the subject of the talk is, well, what the heck is a lens? A lens is a composable notion of a purely functional field accessor. Okay, so we saw how copy didn't compose, but lenses, on the other hand, do. So a lens from A to B has a getter that knows how to get, given an a B out of it, get the value of one of its fields, or get some portion of it. Okay, and it has a setter that knows how, given a B and an A, how to replace that value with the one that we've asked it to set. So we're going to set a B-valued field inside of our head. Okay? So we just defined it, in this case, a case class. So we can actually just pass it two functions. And then we'll just define our getter and our setter to actually apply those two functions for us. So far, so good? So we can ask a lens to get a value, we can ask a lens to set a value. Yes?
Is it important here that it's a case class that stores function values rather than just an abstract class?
You could just use an abstract class. I use the fact that it's a case class to write them more succinctly. However, you could just use an apply method to actually build it.
And the setter returning an A
is important because we didn't actually mutate our A. We constructed a new one for it. Right. So this is going to well, I'll show you a couple of examples in a minute. But the idea is that we're going to take an A, take a B that we want to set into it, and we're going to build you a new A. Or here we're just getting the B out. There's no side effects, right? We're in pure functional programming land. So a program that returns unit is pretty boring. So in order to have these things be sensible, I want to put some laws on them. Okay? And the first law is that if I set some field inside of A to B, and then I go get that field back out, I should get what I set. Okay, that seems like a perfectly reasonable constraint. And second, if I set some field to B, and then I set it again to a new value, I should get the latest thing that I set. Okay? So that's just kind of saying that I flushed out whatever was there. I'm not accumulating with a setter or anything like that. I'm actually setting and changing. And then finally, that if I get the value that A currently has for a given field, and then I set it right back, I don't actually change the meaning of A in any way, shape, or form. Right? So if I get and then set immediately, I don't change A. I don't break any properties of it. Okay? And so with these three laws, these three tools for equational reasoning, we can actually take our lenses and sort of reason about the results. And we can say that it's safe to compose lenses in certain interesting ways, which we'll start playing with.